All right, hey everybody, happy Friday. We got section 6-7, which is called using trigonometric ratios. We're finally going to use these trigonometric ratios in kind of like real world context or real world situations, right? Because as you can tell, if you're somebody designing something or trying to figure something out about the space around you, you might want to use angles and the measurements you can get to help make your calculations a little easier. So one question you'll have for homework tonight is, it's pretty easy actually to use a tool called the Clinometer to figure out the angle, something called an angle of elevation of where you're standing. So say this is a 57-degree angle. And then it's really easy to use just a tape measure to figure out how far away you are from a building. To do that in order to determine the height of a building, for instance, the height of a building here. So trigonometry is used right just out there, right? You can just do a simple tool called a clinometer, a tape measure, boom, you can figure out the height of any building. So anyways, hopefully by the end of this lesson, you would know how to do something like that here. Okay, using trigonometric ratios, we're going to talk about this language that we have up top here. They're really just two vocabulary words new in this new section because we already know sine, we know cosine, we know tangent, right? We know what theta means in terms of a reference angle. So we know how to solve for things using right triangles. But as we know in our day-to-day lives, triangles aren't kind of neatly wrapped up for us in terms of, oh, here's a triangle here, here's a triangle here, here's a triangle here. There are triangles everywhere, all around us. We just need to find where they are. And here's a situation right here, okay, where in real-world context, we might want to know what some vocabulary is, what we can refer to in order to see those right triangles, to be able to solve things. And get certain lengths of things. Other things we might want to know as human beings, how far away we are from things in terms of figuring out here, okay? So I'm going to transition away from this here. This is the whole section. Very, very quick section right here. Not much to read, not much to be said right here. They really just want you to know these vocabulary words. I'm going to take it kind of all through this right now, which we have up on our slides right here, okay? So definitions. What we want to get to on this slide here are those two definitions that I previewed a second ago in section 6-7 in your textbook. Okay, here's the premise of this leading up to the definitions here. Okay, so this is the example they explain. I'm just going to do the same one for you so we're both working off of the same thing here. Okay, here's the premise. Suppose an operator at the top of a lighthouse. Here we have a lighthouse, right? We live near an ocean. I don't know if there are any lighthouses near us here that you guys have visited growing up. But anyways, lighthouse is over there on the beach. Okay, there we go. We got the light going out. Light going out straight horizontal to the ground, I guess, here. But as a lighthouse operator, you might have to look a certain direction, okay? So we have our lighthouse operator. He's at top of the lighthouse right there. There's that gentleman right here, lonely lighthouse operator, just staying there all by himself all night, okay? He looks off into the distance, okay? Looks off into the distance. And how's he looking to start with, okay? Well, generally, right, he's not looking anywhere in particular because there's nothing much to look at. You're a lonely lighthouse operator, okay? So he's just looking out on the distance, okay? And so the basic idea about where we look, right? Where we look in life, typically, if you have to look at your default place you look ahead, right? You look ahead. What does ahead mean in terms of geometry? Okay, I'm looking ahead right now, looking ahead. I'm not looking quite ahead, I'm looking down, I'm looking down, right? Down at the computer screen, okay? Looking ahead means looking at the horizontal, okay? Looking at the horizontal. Horizontal to what? Horizontal to the ground, right? To the ground, okay? So in most situations in life, we're walking ahead, right? We're walking down the hallway at school, we're looking forward, but we're looking horizontal to the floor of the school, which is a flat surface. Oh, wait, the earth is not flat. Okay, all right, so anyways, in this situation here, in these trigonometry problems, we're going to assume the earth is flat. The earth's curvature is insignificant to these particular problems here, okay? So anyways, the default way, so one thing I need to clarify for you in terms of how these problems get set up is that by default, right, typically we as human beings look forward. That means horizontal to the ground. We look parallel to the ground here, okay? So this lighthouse captain typically looks forward because he doesn't know where the boats are, and then, well, if he looks down, right, he's looking down at a 2-degree angle from the horizontal. Okay, and what that's called is the angle of depression. Okay, angle of depression. There's your first vocabulary word. That's why it's bolded out. Put that into your notebooks. The angle of depression is the angle from the horizontal that a person looks downward. Okay, it's not written out like that in the book. It's not looking right there. It's not written out like that there in the slides. But I've just said it for you right now, and you should write it down too. The angle of depression is the angle from the horizontal, and hopefully you just kind of you feel in your bones what from the horizontal means. Downward, okay, downward here, okay? This is a little bit different, right? So if I have to think about a 2 degrees, so let's maybe think outside the box here about more angles of depression. If I look at a 2-degree angle of depression, so here I'm looking forward, right? I'm looking at the horizontal. If I look 2 degrees angle of depression, it's not much downward. I looked just a little bit here, okay? So he tilts, he's looking forward, he tilts his head just a tiny bit here. So quick question, guys. What is in this case here, what would be a 90% angle of depression? What would that be? So I'm looking forward, looking at the horizontal. A 90 degrees, just try to picture that because you'll have to do angles of depression. You have to say angle of depression in your problems today. If I look at a 90-degree angle of depression, where am I looking? Yep. I'm looking down at the floor, straight down, right? Straight down, okay? So here, 45-degree angle of depression, 0-degree angle of depression. I'm looking at the horizontal. This would be looking straight down, okay? So if he were to say drop something on the floor right below him and he'd look down, he'd be looking at a 90-degree angle of depression here, okay? So even just a slight 2 degrees out, he can spot something pretty far away because a 2-degree angle is not a very big angle, okay? So there's one vocabulary word that comes up in today's problem set, and it comes up a lot of trigonometry problems here. Okay, here's another one here too. We got Captain Hook. He's looking up. So remember, if you're up top and you're looking from the horizontal downward, called angle of depression, obviously the opposite of that. Well, I didn't ask you, well, what would a negative 90-degree angle of depression be? Oh, that's something to think about here. Okay, wait a second. Go back to angle of depression for a second. If I look at just a positive 90-degree angle of depression, I'm looking down there like that. We haven't talked about negative angles yet, but they do get defined at the very end of the book. I don't know if we'll get there. But if you had to look at 90-degree angle of depression, you're looking straight down. What would a negative 90-degree angle of depression be? Straight up to the sky. Mr. Sun at noon, right above there. Okay, so the angle of depression is with respect to the horizontal. You look downward if it's positive, right? Angle of depression downward. You look upward if it's actually negative. If you have a negative angle of depression. Guys, this starts to get thinking is that why should the default be that way? If a negative angle of depression is you're looking upward, let's come up with a different name of this. Okay, so from the horizontal, again, Captain Hook, he's looking forward. He's trying to get to that land that's somewhere off there. Oh, he wants to see he sees the lighthouse there. He wants to look up at the light. He wants to look at the light there. He wants to figure out his long-lost friend who's right there. Is that Peter Pan? No, I don't know. Peter Pan doesn't smoke, what is that there? A pipe or something like that? I don't know. Anyways, the opposite of looking down is obviously looking up, okay? So that's called an angle of elevation, okay? Angle of elevation. A 2% angle of elevation, okay? What's a 90% angle of elevation? 90% of angle of elevation would be straight up, okay? Straight up, because it's the angle that you make with the ground, okay? With the ground. We got our bottom, so if this is our horizontal, we look up, that's an angle of elevation. If this is our horizontal, and we look down, that angle that gets made is the angle of depression, okay? So positive angle of depression, positive angle of elevation, okay? Now this seems pretty straightforward, but there are words that come up, and I'll show you some examples that I always get questions on, which hopefully make a little more sense before you jump into the problem set today. Okay, so trig problems are commonly presented using these vocabulary words. They're in your problem set today, and hopefully I laid it out for you here. Okay, so let's move this one over here. Let's actually do this as an example problem. Kind of, they do this in the actual lesson here. We'll do it kind of together right now. But anyways, let's use this scenario to solve a problem. If the lighthouse operator's eyes are exactly 25 meters above sea level, how far away is the boat from the base of the lighthouse here, okay? Quick tips on solving problems like these is label it up, right? Sketch out your diagrams, draw it out here. So in your notes, maybe you're sketching out this particular situation. We have an angle of depression here. We have an angle of elevation. There are a few ways we can solve this. I think maybe we'll put our theta over here, okay? Because this is gonna involve the lighthouse here, okay? We're given our theta here is 2 degrees. That's our angle of elevation, okay? The height of the lighthouse, that's what we're going to use to help us solve for what x is here, okay? So this problem here, if the lighthouse operator's eyes are exactly 25 meters above sea level, okay? So from here to here, got 25 meters, okay? And what do we know about the lighthouse too that's sort of not explicitly said in this problem? Well, would the lighthouse be at an angle to the ground that's anything other than 90? No, the lighthouse is perpendicular to the ground itself here, okay? So I want to put in that perpendicular symbol. So here we have a right triangle, right? We have a right triangle right here, okay? We have a 25-meter side, right? Looks like a leg because our right angle's right here. Looks like a leg. If this 2 degrees is our reference angle, is that the opposite or the adjacent side? Okay, this is our opposite side, okay? This here, from the distance from the actual lighthouse operator to Captain Hook, right, the captain of the sailboat, that would be the hypotenuse. Okay, this is our hypotenuse right here. Okay, and then that means x is going to be the adjacent. Okay, the adjacent side. Okay, one other thing that I forgot to mention on the last slide here that I think is worthy of putting in this particular situation, the angle of depression from this lighthouse operator is the same as the angle of elevation, right, with respect to this Captain Hook, right, the captain of the sailboat here, okay? Why can we think about why that actually is for a case here, for sense here? Well, if we think about it, this sailboat is also perpendicular to the ocean, right, perpendicular to the ocean, perpendicular to the grounds, okay? So anyways, this is also at a right angle right here, okay? So those two lines are parallel, okay? Those two lines are parallel, so because they're both perpendicular to the ground, they're perpendicular to the same line in the same plane. So anyways, these are both parallel, okay? So then why is this angle of depression 2 degrees and that angle of elevation also 2 degrees? Because you'll see this, the angles of depression from a given reference point, the same as the angle of elevation from the other reference point in the situation. Well, they're the same because they're what types of angles, right? The 2 parallel lines are cut by transversal, and then alternate interior angles are congruent. So anyways, just figured I'd mention that here. Okay, back at the task at hand, we want to solve for x right here, okay? We want to solve for x. Well, we know the opposite side. We want to know the adjacent side. We have a reference angle. So now we got to go through our SOHCAHTOA. Okay, SOHCAHTOA. Are we going to use the sine ratio here? Well, sine is opposite over hypotenuse. Okay, so we know the opposite, don't know the hypotenuse. We could solve the hypotenuse using the sine. Does that help us? Does that help us get x? It could get us closer to x, but I think we want to use a tangent ratio where the adjacent sides involved. So let's throw away sine. The cosine, right? Cosine, cosine is adjacent over hypotenuse, okay? So here, adjacent, do I know that? No, that's what I'm trying to find. Do I know the hypotenuse yet? No, I don't want to spend time getting that either. So you know what? I'm going to throw away the cosine because I don't know the hypotenuse. What if I have a trig ratio, one of the ones we've talked about so far, that involves the opposite side, which we know, and the adjacent side, which we are trying to get, right? Or trying to get here, okay? Would that work? Yeah, I think so. I think that would work here, okay? So, right, the tangent is TOA, right? TOA, that's when we remember what the tangent ratio is here. SOHCAHTOA, get it right. Remember it, make friends at college parties. When you get to college, wait, take your time. No reason to crash those as high schoolers. No, that's, I don't know if you know geometry, you can get into a college party just fine. All right, anyways, check it out here. Tangent of 2 degrees would equal, right, the opposite over adjacent ratio here, okay, so opposite over adjacent, and then we got 25 meters, okay, over x, okay? I think you guys should all be able to solve a problem like this, right, and get it through here, okay? Tangent of 2 degrees, let me pull up my trusty 2020. The book just says use page 271. That's because that book came out in 1985, before home computers really were a thing at all, unless you had like millions of dollars. But anyways, tangent, get rid of my second book, and make sure you're in degree mode. It says rad. Okay, good, because if I hit rad shows up there. No, I don't want rad, I want degree. There we go. Hit a tangent button, boom, we get this. Okay, so remember, we can do a mean swap in this situation. That's typically how I do it. Okay, this is tangent of 2 degrees over 1. This is 25 over x. So hey, I can swap my means, or I can flip both fractions, do a mean swap, and that could help me too. But anyways, I'm just gonna do an extreme swap right here. Okay, so I'm gonna do x equals 25 over tangent of 2 degrees. Okay, I wonder if this actually lets you save your answer in this one here. I guess it doesn't. We'll just have to memorize this and get an approximation, okay? 0.03492, 0.03492. So I'm going to do 25 divided by 0.03492. I hope I did that right. And I get 715, okay? So about 716 meters. Okay, that's one way to solve it. Hey, another easier way to solve it, which they actually go through in the book, check it out here. Let's not do this method with you, but just a reminder that you can do this. If you have a right triangle, you can figure, and you don't like solving it this way, right? You forget doing that extreme swap and whatnot here. You can actually solve it this way. If I know this is a 2-degree angle right here, well, I know that this is, of course, perpendicular. Okay, perpendicular, the lighthouse perpendicular to the ground. This is going to have to be an 88-degree angle. Okay, 88. And again, I have trouble writing with this big pen on the PDFs here. Okay, so you could have used this, right? This 88 angle, this one that's complementary to the 2-degree angle. This is a acute angle. The acute angles of a right triangle complementary. So you could use tangent of 88 to say x over 25 meters, and that would have been another way to solve here. Okay, what you notice is, again, things get kind of imprecise with trig problems, so they get kind of generous to you in this problem set. You don't really need to worry about getting super precise answers with this trig stuff, okay? You can just say about 700 meters, right? So they're actually not being very precise at all, okay? So anyways, angle of elevation, angle of depression, those are really your vocabulary words today. You got a few more things. I don't know if I'm going to go through too much more stuff. I might film a separate video about this. But anyways, you're going to do some of these problems today with your groups in the Desmos problem set, okay? So we'll give them to you, we'll give them a shot, then you'll have a problem set for homework, okay? And that's about it, okay? Another thing I wanted to say here, guys, start thinking about how these things could get used in real life, because, you know, I told you earlier, this is something that you could do pretty easily, is figure out how tall a building is here, okay? We're not going to send you to downtown San Francisco to figure this out, but maybe in future years I would. There's not a pandemic going on. But there's a tool actually called a clinometer. It's called a clinometer that allows you in real life to get a pretty good angle of elevation, okay? Angle of elevation. Let me show you what a clinometer is real quick here. Here's a clinometer over here. I searched for it on Google earlier. I've actually never used one of them, but it's a really easy tool, So check it out here. How to use a clinometer. Looks like this. It's just a protractor using gravity, right? So it's using a string, right? String, of course, to the middle of where it's at 0 degrees, right? Or just the sort of vertex of where angle's being created here. Creates gravity, of course, is going to pull a string perpendicular to the ground. Okay, perpendicular to the ground. So you can tell your angle of elevation, okay, if you look up along the protractor, like this side of the protractor right here, that string is going to stay perpendicular to the ground, okay, perpendicular to the ground. So if you fasten it, if you save it here, right, let's say this is about 15 degrees off of the 90 degrees right there, that would be a 15-degree angle of elevation, okay, angle of elevation. So now you're asking, like, how could I use this in my day-to-day lives? Well, if your job is to figure out how tall a building is, you simply need to go bring your clinometer, stand in a certain spot, look up, okay, and then look at your clinometer, figure out how many degrees off of 90 you are, and then you can go and measure from the spot you're standing to the base of that building, okay, right, to that length right here, okay? So that's why this vocabulary is important, is because angles of elevation and depression, they're measurable, and they can use us to solve problems, which you'll see in the problem set, okay? Thanks for watching, guys. I will see you on Monday, and hopefully you're working on your problem set today with your groups. Bye.